Imagine traveling 220 days across the solar system to a place where no man or woman has ever gone before. Being at your destination for one day and traveling 280 days back home. Good afternoon, ladies and gentlemen. My name is Thibaut Beschor. This is Lawrence Kandel, and we represent Team Adrestria. Our vision is to inspire humanity by making the first steps to setting a footprint on Mars. And we did this by designing an end-to-end flyby mission to Mars for a crew of 2 as safe, simple, and cost-effective as possible. Before we start, let me give you a brief introduction of what we're going to do today. We're going to start with introduction, then we're going to go to the spacecraft and mission overview. After that, we will discuss the flight systems, and we will conclude with the budget, schedule, and costs. So who are we? Well, we are an international group of students from the Delft University of Technology. We are all aerospace engineers, and we are space enthusiasts. Therefore, we signed up for this competition because we want to do our part in generating a spark which will reignite manned space exploration across the solar system. But to do this, how did we do it? Well, we used system engineering. The first step we did is we did a functional analysis to determine the functional requirements of our mission. After this, we combined them with the top-level requirements, and this left us with the whole requirements for the complete mission. From these, we made our preliminary designs. For example, we had to choose which rockets propelled our system into space. We had to choose between the SLS, the Ariane 5, and the Falcon Heavy, for example. From this, we went into a detailed analysis phase where we traded off options for options. And we realized for our launchers that the SLS was not useful because of time constraints. The Ariane 5 was not possible because of the payload constraints. Therefore, the Falcon Heavy was the option to choose. From this, we moved into a detailed design where we would break up the whole mission into subcomponents, run it through the analysis again, and come up with the final design that we are presenting to you today. Now that we've discussed how we did it, we can now discuss what our mission actually is. Our first step was to verify the trajectory. We had to leave on January 2018. We used our own in-house software, 2DOT, to create a pork chop plot of our trajectory. And as can be seen, the dark blue areas require the least amount of delta V. And on January 2018, we have around 500 days of travel. From this, we realized that we had to make a trade-off between re-entry velocity or decreasing your amount of delta V at start. We realized, working together with the re-entry team, that our maximum re-entry velocity would be around 14.2 kilometers per second. Therefore, we optimized for 14.2 kilometers per second to decrease our delta V as much as possible so we can decrease the fuel required in LEO. From this, we arrived to our final trajectory, which is basically we depart from Earth on the 4th of January 2018, we fly by Mars on the 20th of August 2018, and we arrive back on Earth on the 20th of May 2019. Our trajectory is summarized in this table. As we can see, our TMI is 4.857 kilometers per second. Our margin flyby altitude is 100 kilometers. The re-entry velocity is 14.2 kilometers per second. And the mission duration is 501 days. Now that we've verified the trajectory, we need to give you an overview of our spacecraft before we can actually talk about the mission. Well, our spacecraft consists of a Dragon Rider capsule. This is used during re-entry and launch. Behind the Dragon capsule, there are 2 SpaceX Dragon trunks extended. These are pressurized, and they will be used for the main journey of our mission, as well as they will be used post-mission, but this will be explained later in the presentation. There are 4 solar arrays attached to our spacecraft. These are retractable when we're in LEO orbit, as well as we are in the Martian atmosphere, or flying by Mars, to reduce damage to the solar arrays. And they are adjustable, therefore no matter what orientation the spacecraft is, it will always be pointed towards the sun. Finally, we have a main propulsion stage. This is a Falcon Heavy second stage. It is important to note that our whole spacecraft is SpaceX, therefore it is compatible with the Falcon Heavy launcher. Therefore no extra modifications need to be made in order to make our spacecraft fit on the Falcon Heavy launcher. From this now I can give you a brief overview of our mission. Our mission consists of 2 launches. The first launch is the launching of a fuel depot into LEO orbit. Once this is done, the crew, along with the spacecraft, are launched in the second Falcon Heavy launch. This is also launched into space. It is important to note that the second launch the launcher is fully filled with fuel, therefore once it arrives in LEO, it still has some fuel left over. It is docked with the fuel depot, refueled, and TMI can start, transmarch injection. Once it is started, it flies by Mars at 100 kilometers altitude on the 20th of August 2018. Comes back to Earth, jettisons the living module on the 18th of May 2019, and re-enters the Earth's atmosphere on the 20th of May 2019. Now, the launch. We had two main possibilities for the launch. We could either do a one-stage burn, which required a higher delta V and more fuel in the orbit, or we could do a two-stage burn, which required a high-altitude elliptical orbit, but less delta V. We realized that with our analysis, that if we would do a high-altitude elliptical orbit, the crew, as long as the spacecraft will pass through the Van Allen belt, increasing its radiation exposure to dangerously high levels. Therefore, we did not choose this method, and we stayed with the one-stage burn, resulting in our final delta V of 4.857 kilometers per second. This required a fuel of more than 71 tons. From this, we realized that the Falcon Heavy can only carry 53 tons to LEO. Therefore, we needed two launchers. The first launch is the fuel. It'll launch around 40 tons of fuel into LEO orbit. Once this has been done, the second launch can commence. The second launch is the spacecraft and the launcher, with the launcher being completely full with fuel. Therefore, once the spacecraft is in LEO orbit, there will be the spacecraft and there will still be a remaining 30% of fuel left in the launcher. Then the refueling can commence, refuel the spacecraft back to 100%, and trans-Mars injection can start. Therefore, how do we do this refueling procedure? Well, the first step is to dock the LOX tank to the back of the spacecraft. After that, there is a module decompression of the re-entry vehicle. The crew leaves the re-entry vehicle in the EVA suits and aids in the docking procedure. There are three main reasons why we chose EVA on this space mission. The first is to not expose the heat shield of the re-entry vehicle to the space environment, reducing the risk of damage and reducing failure on re-entry. The second, if damage does occur in space, we can fix it with our EVA suits, go outside, and fix the problem. And finally, the reason why we chose it is because we can aid it in the docking procedure. So the first step is to see if the LOX tank is docked correctly to the spacecraft. After that, they manually collect the RP-1 tank to the spacecraft. Once this is done, they board the main pressurized cabin. Once they're in the main pressurized cabin, they wait for the fuel to be refueled. They disconnect the fuel tank, ignite the thrusters, and orbit insertion can commence. It is important to note that during re-entry, it's the same process, but the other way around. Therefore, they put the EVA suits on, they go into space, enter the re-entry vehicle, pressurize the re-entry vehicle once more, and go back into Earth. Now that I've given an overview of the trajectory, the mission, and the spacecraft, I would like to give the floor to Lawrence Campbell, and he will go into detail about the subsystems. Lawrence?
Thank you, Timo. Well, first of all, let me give you an overview of the different flight systems that we looked at and that we designed in detail. Unfortunately, we don't have enough time to discuss all of them today, so we selected the few that are the most crucial to our design. And those are the environmental control and life support system, the solar flare radiation protection, the guidance, navigation and control, the scientific payload, and the re-entry and landing. Well, first of all, the environmental control and life support system. We had to choose for a non-regenerative system, which basically gave us two options. The bioregenerative system, which uses living organisms to regenerate molecules, and the physical-chemical system, which uses physical, chemical, and mechanical processes to renew molecules. It turned out that the physical-chemical system had a lower mass and a lower volume for our mission. To further design our ECLSS, we studied a paper performed by Dr. Hanford in 2005, in which he made multiple designs for ECLSS. And one of them was the Mars Transit Vehicle. Well, we modified and scaled this design to our mission, and we came up with the following figures. As you can see, on the left-hand side is the weight of the consumables, and on the right-hand side is given the weight of the consumables combined with the hardware associated with this consumable, or the equivalent system mass. Well, if we look at the weight of the water, it's only 350 liters. But in our actual calculations, we saw that we needed 650 liters. But we are using hydrogen-oxygen fuel cells in the LEO phase, and these cells produce about 300 kilos of water, potable water. And this was already accounted for in the power weight section, so we don't need to account for that again in the ECLSS section. Furthermore, we incorporated a free space volume of 10.2 cubic meters for two crew members, which is actually a NASA requirement. Well, now that we are taking care of the crew of the health of the crew from the inside, let's look at the outside, and especially the radiation, because there are two sources of radiation, which are the solar particle events, or the solar flares, and the galactic cosmic rays. Well, when we looked at what is the maximum allowed dose that the crew can sustain, and what is actually the maximum dose that they sustain in space, and we found out that we had to reduce the daily dose by about 6%, and that's mainly caused by the GCR. Furthermore, we have the acute dose caused by the solar flare, and we saw we had to reduce that by about 85%. So how are we going to do that? Well, for the GCR, we have a Kevlar layer around the spacecraft which functions as a micrometeorite and orbital debris protection. But it doubles as a radiation protection, and it reduces the radiation by 4%. Furthermore, we placed our subsystems on the circumference of the spacecraft, which reduced the radiation by another 2.4%, leading to a total reduction of 6.4%, meeting the requirements. Now let's look at the solar flares, because there's one thing that's convenient about the local solar flares, and that's that they come from one direction, the sun. And we designed our spacecraft in such a way that it's pointed with the rear end towards the sun, where we conveniently placed our polyethylene water tanks. And these are made of polyethylene, and they reduce the radiation by 49%. And if you look at the water, the food and waste that's inside, at the beginning of the mission it will reduce the radiation by 43%, and at the end of the ride it will reduce the radiation by 37%, leading to a minimum total reduction of the radiation of 86%, meeting the requirement. Well, this concludes the part concerning the safety and health of the crew. Let's look at the mission system, and one of them is the guidance and navigation and control system. Well, we require a high accuracy system because we are performing a flyby at Mars. Therefore, a ground-based GNC system is not desirable, because as you get closer to Mars, the signal has to travel longer and the system will be less accurate. Therefore, we chose for an autonomous system based on the AutoNav mission, which was on the Deep Space One mission in 1998, and it features a miniature integrated camera and spectrometer. And what it does, it periodically makes pictures of the universe, and by the end of this picture it can determine its position and orientation in space. Furthermore, as we get to the surface of Mars, it switches to a high definition camera, and it can navigate using the surface of Mars. Well, our mission is of great scientific importance, and therefore it's interesting to look at the human factors. And for example, it's really interesting to look at the psychological well-being and the cardiac functioning of the crew members. Furthermore, we can measure the degradation of the bones and muscle during a deep space long-duration mission. Furthermore, it's interesting to monitor the cognitive and emotional adaptation of the crew members. When we are at Mars, we are only 100 kilometers from Mars, so it would be a perfect opportunity to launch a probe which could give us vital information on the surface and the atmosphere of Mars. Furthermore, as I told before, we are switching to a MiCast camera, which is taking pictures of the Martian surface, and these pictures are actually of higher quality than any other picture that we have seen of Mars before, because they don't have to be transferred wirelessly back to Earth, but we can bring it back to Earth with our mission again. Further but not least, after our re-entry maneuver, which I will get back to later, we have a post-mission experiment. Our living module will continue its trajectory, and it will continue to measure deep space radiation. We can check out how the degradation of the thermal control system behaves, and we can see how the sustainability of the ECLSS performs. While the re-entry maneuver, let's look at it in a little more detail, because we are arriving at a re-entry velocity of 14.2 kilometers per second. And this actually comes from our determined corridor width, which is 0.04 degrees. And we got this value from looking at other missions. We looked at the Stardust mission, which is the fastest re-entry ever, and that had a corridor width of 0.02 degrees. And because we are a manned mission, we doubled this corridor width, and so that's how we arrived at the value of 0.04 degrees. What this basically means is that if you come in too steep, you will go too fast and you will burn up. But if you come in a too shallow angle, you will skip off and go back into the atmosphere, back into space again. Well, for our re-entry, we set some requirements. We want the peak G-load to stay below 8 Gs, and we want the average to stay below 6 Gs. As for the heat, well, we want the peak heat flux to be below 20 megawatts per square meter, which is actually a characteristic of the Pica X heat shield that we are using. And we want the cabin temperature to stay below 313 Kelvin. Well, let's look at our re-entry if we wouldn't do anything about it. We see that the G-loads would almost exceed 80 Gs. Well, that's way too high, especially if you look at our requirements, which is 8 Gs, the red line. but we're using bank angle modification. We can rotate the vehicle around the velocity vector, and this way we can point the lift vector upwards, downwards, or sideways, and in this way we can control our descent and lower the G-loads. But this comes at a price, because if you lower your G-loads, you're making the total re-entry maneuver longer. So you're generating more heat, which is a cumulative process. So you have to make a trade-off. And we optimized our design in such a way that the G-loads are at a 7.8 G maximum and a 5.81 G average. And the heat generation is 3,100 kilowatts per square meter in the stagnation point. And at the temperature at the cabin at splashdown is 310 Kelvin. Well, now that we've looked at our subsystems in detail, it's time for Thibaut to look at the mass, volume, and power budget of the total mission.
It is nice if our spacecraft has sophisticated subsystems, but the real question is, will it all fit in our spacecraft? Well, we made a detailed budget analysis. As you can see, we looked at the mass, volume, and power of our subsystems. There are two important numbers to look at in this graph. The first is the volume inside of the spacecraft. Our subsystems occupy more than 63 meters cubed of volume within our spacecraft. If we look at this value further, we can see that our available volume is 87.53 meters cubed. Therefore, if we would have a 20% margin on our subsystems, we would still have 11.68 meters cubed volume of free space left over. And this does not include the mandatory free space required by the ECLSS system. Therefore, if we would add those two values together, we would have more than 21 meters cubed of free space within our spacecraft. This is highly beneficial for the mental well-being of the crew, as well as the scientific payload carried on board. The next vital number is the total mass of the spacecraft. Without a margin, it's more than 14 tons, and with a 10% margin, it is 15.5 tons. This 10% margin was taken into consideration due to discrepancies later on in the design process. Therefore, with this mass, it is possible to send it to LEO, from LEO perform a trans-Mars injection, and arrive with the crew safely back on Earth, completing the mission. Now that we've discussed that the subsystems all fit within our spacecraft, we have to look at the schedule and the cost of our mission. The first is the schedule. The first three phases of this schedule has been done by us. Phase 0, we determined the requirements. Phase A, we looked at if it was actually feasible. And Phase B is a report we handed into the Mars Society, is a preliminary definition of our mission. So, the preliminary design of our mission. From this, if this design is considered to be correct, we can move into the detailed definition, where we will make a detailed design of all subcomponents of our spacecraft, as well as a maintenance, integration, and testing plan of all our components. As you can see, the time that it takes for each milestone in the schedule is explained on the top right-hand side. Once this is done, we can go into Phase D, which is qualification and production. This is the longest milestone or production phase, mission phase of our complete mission. At this phase, we look at all the spacecraft components, we see what needs to be modified, modifies it, test it, integrate it, and this phase is done once we have two launchers ready to be launched, one to fuel, one to spacecraft, completely integrated and tested, ready for launch. Phase E is a utilization phase. This basically commences with the launch. Halfway during this phase is the flyby by Mars, and it finishes off with the re-entry and the retrieval. What is important with our mission is that we have a final phase, Phase F, the post-mission phase. As explained by Lawrence, in this phase is when we send the living module on a continuing trajectory around the solar system. And this phase will be used to monitor all the data, which Lawrence says, and it will be vital for future manned space missions across the solar system. Now that this is done, we can discuss the cost. How much will this mission actually cost? Well, we use two cost estimating methods. The first is the advanced mission cost model, and the second is the trans-cost model. From these two models, we came up to a final cost of more than $5.7 billion. If we look at this cost more into detail, we can see the cost progression through the years. As you can see, between 2015 and 2017 is where the major cost takes place. This is due to the qualification and testing of all components. Once the mission starts, the cost will decrease, but it is important to note that after the mission is finished, we still have Phase F, the utilization. Therefore, this phase requires low cost to keep a living module circling around the solar system. Now that we've discussed our mission, I can conclude. So, what have we done? We first had a vision. From this vision, we did system engineering to find the best designs possible to satisfy this vision. We made a trade-off, saw what worked, what didn't work, and ended up with a design. From that one design, we went deep into subsystem design and see what needed to be modified, and if the design will actually work, and if you can actually send a crew to Mars. And we arrived with our final design, Adrestria. But this leaves one question. Why the name Adrestria? Well, for those of you who know Greek mythology, knows that Mars is named after Ares, the Greek god of war. Every time Ares went into battle, he was always accompanied by his two sons, Phobos and Deimos. But Ares had a third child, and her name was Adrestria. Therefore, at a point in this mission, she will finally be standing side by side with her brothers, and together with humanity, glance at the greatness of Mars. Thank you. I would like to invite my team up for the question session.
Yes, please. Scott, you have a question?
Yeah, the schedule went by a little quickly. Can you bring that back up and just show me again how long phase CD is?
C is from the 1st of November 2014 to the 1st of September 2015. And D is from the 1st of September 2015 to the 30th of December 2017.
Okay, so just a shade less than 3 years.
Yep.
Okay.
Question, what was the basis of your cost estimate?
I did cost estimation, and
You have to turn it on.
I used this one. First of all, I used the advanced cost mission model developed by NASA, and afterwards I used the transcost 7.0, and then I looked at a combination of those two to see what cost I got from the advanced mission cost model and from the transcost, and it was around 18% difference. So, but what actually is your question about the basis of the cost?
Well, for example, you're using the Falcon head,
Yeah,
and you're not paying for the development of the Falcon head, you're just paying for launch.
yes, yes.
So, two of those would be a rather small part of $5 billion. So where's the rest of the money?
The main part of the money is going to the development of the living module, the purchase of the re-entry vehicle, and the adaptation of the new heat shield. And the other part is the main part is going to operations. And the refueling module that has to be cooperation with SpaceX, that has to be done. So.
Other questions?
Could you comment on your decision to include the EVA on the critical path, including as part of being able to come back home?
Could you repeat the question?
You had to go do an extravehicular activity to get the crew from, well, both from the Dragon to the living module to begin with, and then from the living module back into the Dragon at the end of the mission.
Well, since the configuration for the spacecraft is as we shown, the crew could not go directly from the capsule to the living module. The only way we could solve this is either by separating the capsule and and docking it to the living module without needing an EVA then, but then we would leave the heat shield exposed to the whole mission, to any micrometeorite impact or any deterioration of the shield. For that reason, and also that we needed the EVA to safely perform the fueling procedure, we decided to have a EVA, as well as maintainability of the spacecraft through the whole mission.
Let's see, a couple questions. So, look like you're in a sense using some heritage equipment, stuff that's flown or about to fly, and then, but you adapted it reasonably. You adapted it from, in some sense, a much different mission, right? One of these things now has to have a hatch and behave like an airlock, and the entry speed is double what LEO entry speeds are. So, how did you accommodate both in your cost and in your mass the uncertainty of these adaptations of heritage systems to these new requirements? Do you see what I'm saying? Did you take that into account, and how'd you do that? How'd you estimate that?
About cost, or yeah, we incorporated 45% margin. That's included in this cost.
Okay.
And we have another like 35% of our, yeah, in case something doesn't go as planned. So
How about the mass and the complexity?
We didn't specifically incorporate a margin for that, but in general, we incorporated a 10% margin because the actual vehicle mass was around 14 ton, and we are calculating with a value of 15.5 ton. So we took actually 10%.
Okay.
Actually, during the design process, we used ESA margins, and then after that we applied another 10% margin to the ESA.
Okay.
Any other questions?
Yeah, if nobody else does, I have one more. That you pick, did I read right, your total mass was about 70 tons, 71?
Fuel
Pounds?
Fuel mass.
Oh, fuel mass, okay, okay. How did you, no, that answer, then I was reading the wrong number, so I got my answer.